Chapter 9, Virtual Memory Management. We're going to describe the benefits of a virtual memory system, to explain the concepts of demand paging, page replacement algorithms, and allocation of page frames, to discuss the principles of the working set model. 9.1 Background. In this background, virtual memory involves the separation of logical memory as perceived by users from physical memory. This separation allows an extremely large virtual memory to be provided for programmers when only a smaller physical memory is available. When we say physical memory, it refers to the actual RAM. Virtual address space of a process refers to logical or vital view of how a process is stored in memory. Typically, this view is that the process begins at a certain logical address. In this figure, we allow the heap sort to grow upward in memory as it is used to dynamic memory allocation. Similarly, we allow for the stack to grow downward in memory through successive function calls. The large blank space or hole between the heap and stack is part of the virtual address space, but will require actual physical pages only if the heap or stack grows. Virtual address spaces that include holes are known as sparse address spaces. Using a sparse address space is beneficial because of the holes can be filled as the stack or heap segment grow, or if we wish to dynamically link libraries during progress execution. In addition to separating logical memory from physical memory, virtual memory allows files and memory to be shared by two or more processes through page sharing. System libraries can be shared by several processes through mapping of the shared object into a virtual address space. Although each process considered the shared libraries to be part of its virtual address space, the actual pages where the libraries reside in physical memory are shared by all the processes. Typically, a library is mapped read-only into the space of each process that is linked with it. Similarly, virtual memory enables processes to share memory. Virtual memory allows one process to create a region of memory that it can share with another process. Process sharing this region consider it part of their virtual address space. Virtual memory can allow pages to be shared during process creation with the fork system called the speeding up process creation. In 9.2, demand paging, commonly used in virtual memory systems. With demand paged virtual memory, pages are only loaded when they are demanded during program execution. Pages that are never accessed are thus never loaded into physical memory. A demand paging system is similar to a paging system, with swapping where processes reside in secondary memory, usually a disk. When you want to execute a process, we swap it into memory. A demand paging system is similar to a paging system with swapping, where processes reside in a secondary memory, usually. Demand paging system is similar to a paging system with swapping, where processes reside in secondary memory, usually a disk. When we want to execute a process, we swap it into memory. Lazy swapper never swaps a page into memory unless that page will be needed. Use of the term swapper is technically incorrect. A swapper manipulates entire processes, whereas pager is connected with the individual pages of a process in connection with demand paging. In this In this 9.2.1 basic concepts, decreasing the swap time and the amount of physical memory needed. When a process is to be swapped in, the pager guesses which pages will be used before the process is swapped out again. Instead of swapping in a whole process, the pager brings only those pages into memory. The valid-invalid bit scheme can be used for this purpose. When this bit is set to valid, the associated page is both legal and in memory. If the bit is set to invalid, the page either is not currently on the disk. The page table entry for a page that is brought into memory is set as usual, but the page table entry for a page that is brought into memory is set as usual, but the page table entry for a page that is not currently in memory is either simply marked invalid or contains the address of the page on disk. Notice in the figure, the marking in the page table invalid bit will no effect if the process never attempts to access the page. Hence, valid bit only those pages that are actually. Notice in the Notice in the figure, the marking in the page. Notice in the figure, the marking in the page table, the invalid bit will no effect if the process never attempts to access the page. Hence, valid bit, only those pages that are actually needed the process will run exactly. What happens if the process tries to access a page that was not brought into memory? Its access to page marked invalid causes a page default. The paging hardware, in translating the address through the page table, will notice that the invalid bit is set, causing a trap to the operating system. This trap is the result of the operating system's failure to bring the desired page into memory. The procedure for handling this page fault is straightforward. We check an internal table, usually kept with the process control block. For this procedure, the procedure for handling this page fault is straightforward. We check an internal table for this process to determine whether the reference was a valid or invalid memory access, usually kept with the process control box. The procedure for handling this page fault is straightforward. We check an internal table for this process to determine whether the reference was a valid or invalid memory access. Second, if the reference was invalid, we terminate the process. If it was valid but we have not yet brought it in that page, we now page it in. Third, we find a free frame. Fourth, we schedule a disk operation to read the desired page into the newly allocated frame. Fifth, when the disk read is complete, we modify the internal table kept with the process and the page table to indicate that The page is now in memory. Sixth, we restart the instruction that was interrupted by the trap. The process can now access the page as though it had always been in memory. In this extreme case, we can start executing a process with no pages in memory. When the operating system sets the instruction pointer to the first instruction of the processes. In these extreme cases, we can start executing a process with no pages in memory. When the operating system sets the instruction pointer to the first instruction of the process, which is a non-memory resident page, the process immediately faults for the page. In this extreme case, we can start executing our process with no pages in memory. When the operating system sets the instruction pointer to the first instruction. In this extreme case, we can start executing a process with no pages in memory. When the operating system sets the instruction pointer to the first instruction of the process, which is a non-memory resident page, the process immediately faults for the page. After this page is brought into memory, the process continues to execute, faulting as necessary until every page that is needed in memory. At that point, it can execute with no more faults. Pure demand paging never brings a page into memory until it is required. The hardware to support demand paging is the same as the hardware for paging and swapping. In 9.2.2 performance of demand paging can significantly affect the performance of a computer system. To compute the effective access time for a demand paged memory. For most computer systems, the memory access time, denoted MA, ranges from 10 to 200 nanoseconds as long as we have no page if no page faults is effective. As long as we have no page faults, the effective access time is equal to the memory access time. However, a page fault occurs. We first read the relevant as long as we have no page faults, the effective as long as we have no page faults, the effective access time is equal to the memory access time. However, if page fault occurs, we first read the relevant page from disk and then access the desired word. Let P be the probability of a page fault, where 0 is less than or equal to P probability less than or equal to 1, where the formula of the effective access time is equal to 1 minus the probability of a page fault times memory access time plus probability of a page fault times page fault time. To compute the effective access time, we must know how much time is needed to service a page fault. A page fault causes the following sequence to occur. Trap the operating system. First, trap the operating system. Second, save the user registers and process state. Third, determine that the interrupt was a page fault. Fourth, check that the page reference was legal and determine the location of the page on the disk. Fifth, issue a read from the disk to a free frame. Wait in a queue for this device until the read request is serviced. Wait for the device seek and/or latency time. Begin the transfer for the page to a free frame. Sixth, while waiting, allocate the CPU to some other CPU. Sixth, while waiting, allocate the CPU to some other user. CPU scheduling is optional. Seventh, receive an interrupt from the disk input or output subsystem. Save the registers and process the state. 8. Save the registers and process state for the other user. If step 6 is executed. 8. Save the registers and process state for the other. 8. Save the registers and process state for the other user if step 6 is executed. 9. Determine that the interrupt was from the disk. 10. Correct the page table and other tables to show that the desired page is now in memory. 11. Wait for the CPU to be allocated to this process again. 12. Restore the user registers, process state, and new page table, and then resume the interrupted instruction. Not all of these steps are necessary in every case. In any case, we are faced with three major components of the page fault service time. Service the page fault interrupt, read the page, restart the process. These tasks may take from 1 to 100 microseconds each. The page switch time, however, will probably be close to milliseconds. A typical hard disk has an average latency of 3 milliseconds, a seek of 5 milliseconds, and a transfer time of 0.05 milliseconds. Thus, the total paging time is about 8 milliseconds, including hardware and software time. In computing the effective access time, in this solution is it is rare from the book, and I also made my own solution that is simple or easy to understand. Effective access time is equal to 1 minus the probability times the effective access time is equal to 1 minus the probability times the memory access time plus the probability times page fault time. Our page fault time is the 8 milliseconds. As we convert it into nanoseconds, it gives us 8,000 800 it gives us 800,000. Effective access time is equal to 1 minus the probability times memory access time plus probability times page fault time. Then, where our page fault time, effective access time is equal to 1 minus p probability times memory access time plus probability times page fault time, where our page fault time is 8 milliseconds, where we convert our milliseconds into nanoseconds. It gives us 8 million. After we convert it, effective access time is equal to 1 minus p probability times memory access time plus p probability times page fault time, where our page fault time is 8 milliseconds. I convert this multiplication asterisk to a parenthesis where I convert this multiplication, the asterisk symbol, into parentheses so that we can see it clearly and we can do a distribution in a distributive law. Before we do a distributive law, we should convert this first milliseconds to nanoseconds. It gives us 8 million. After converting milliseconds to nanoseconds, we do the distributive law, where 200 times p and 200 times 1, then 8 million times p, where the result is this one. After distributive law, we can do a factorial, where I did put a bracket to do a factorial, where we can see that there are p in 200 and p in 8 million. I also put parentheses, so I also put parentheses so that it can easily be understood. So as you notice, I also put a parenthesis after a distributive law. As you notice, I also put a parenthesis after a distributive law so that we can see it properly rather than doing this multiplication and asterisk symbol. So in doing the factorial, we pick out this p inside of the bracket and leave 200 plus 8 million. Then the result is this, where we can subtract 200 minus 8 million. Then we got a negative 7,999,800, where we could also distribute the negative p and the negative 7,999,800. As you noticed that the sign negative or minus in here to then distribute negative 7,999,800 to minus p or negative p. Then we have positive or plus 7,999,800 times the p. Then we will do it back in this original form where in the book.
So the next topic is the copy on write. Copy and write allow both parent and child process to initially share the same page in memory. If either process modifies a shared page, only then is the page copied. It also allows more efficient process creation as only modified are copied. So this example here is this diagram. So here we have a process 1 physical memory and the process 2. In process 1 and process 2 is accessing the physical memory and sharing each other of the data. So is accessing the page A, B, and C. So before pa nasa process 1, wala pa niya gi-modified ang C. So muna yan siya ang mga system calls nga magamit ato nga diagram. So first is the fork system call. It creates a child process that is duplicate of its parent. It also creating a copy of the parent address space for the child, duplicating the pages belonging to the parent. Next is the exec system call. It immediately after creation, the copying of the parent address space may be unnecessary. The operating system will create a copy of this page, mapping it to the address space of the child process. Child modifies only copied page, not only on the belonging to the parent. All unmodified pages will be shared by both the processes. So mo to siya gaina. So gaina is ang process 1 kay wala pa niya gi-modified ang page C sa physical memory. So now gimodified na niya ang page C sa process 1 na pod. So all unmodified process are kato lang ang ilahang physical memory. So kung ang process 1 gimodified niya ang C, maghimo siyang duplicate para siya ra isa maka-access ana nga physical memory or the page. Page that cannot be modified can be shared by the parent and child. So balik ta. So katong wala daw nga wala na modified nga C, aning copy of page C. So katong wala gigamit nga wala siya nag-modified, mura gyapon ilang pag-access sa physical memory. They sharing also the data. So copy and write is a common technique used by several operation systems. It includes the Windows, Linux, and the Solaris. Pages used to satisfy copy and write application are typically allocated using zero fill on demand, meaning that their previous contents are zero out or before the copy proceed. Some systems provide an alternative to the fork system call called the virtual memory fork or VFork. In this case, the parent is suspended and the child uses the parent memory pages. This is very fast for process creation, but it requires that the child not modify any of the shared memory pages before performing the exec system call. In essence, this addresses the equation of which process execute first after the call of the fork, the parent or the child. With VFork, the parent is suspended, allowing the child to execute first until call exec, sharing pages with the parent in the meantime. So the next topic that we have is the page replacement. Page replacement is talking about or decide which memory pages to page out, or sometimes called a swap out or write to disk, when a page of memory needs to be allocated. It also it happens when our requested page is not in a memory. It is called page fault. So kung wala siya ato nga dito sa memory niya, mutawag siya og page fault. And a free page cannot be used to satisfy the allocation, either because there are none or because the number of free pages is lower than some threshold. So basic page replacement. Page replacement taking the following approach. If no frame is free, we find one that is not currently being used and free it. Next, we can free a frame by writing its content to swap space and changing the page table to indicate that the page is no longer in memory. So, page fault service routine to include page replacement. So, mo siyang steps to the page fault service ilang routine kung saan nimo pag-access ato nga data. Number 1, find the location of the desired page on the disk. 2, find a free frame. If there is a free frame, use it. If there is no free frame, use a page replacement algorithm to select a victim frame. Write the victim frame to the disk, change the page and frame table accordingly. Read the desired page into newly free frame, change the page and frame tables. Then lastly, the restart user process. So we have a table here. So this is the graph or the picture of the steps nga naada ni nga page fault routine. So muna siya. Next is the page replacement is the basic to demand paging. It completes the separation between logical memory and the physical memory. With no demand paging, user addresses are mapped into the physical address. So the two sets of address can be different. Then with demand paging na po, the size of the logical address space is no longer constrained by physical memory. Then we have two major problems here to implement the demand paging. First is we must develop a free allocation algorithm. Second is a page replacement algorithm. So it will evaluate an algorithm by running it on a particular string memory references and computing the number of page fault. The string of memory reference is called the reference string. Also, to reduce the number of data, we can use here is the two facts. First is the given page. So we need to consider only the page number rather than entire address. Second, if we have our reference to a page P, then any of reference to page P that immediately follow will never cause a false fault. So for example, so nasa yung mga string there sa ubos. So at the 100 bytes per page, this sequence is reduced to the following reference string. So nasa ubos 141616166161. So muna siya ang graph sa number of frames under the number of page fault. The first algorithm in the page replacement is the FIFO replacement. FIFO means is the first in, first out. A FIFO replacement algorithm associates with each page time when that page was brought into memory. When a page must be replaced, the oldest page is chosen. So, another picture here is the example of the reference string. Sa page, then nasa reference string. Sa taas mo na siya, reference string. Then, first yung isulod ang 7. So, tanaw niya, empty man ang tanan. So, mabutang siya og fault, page fault. Kaya may sulod. Then, next is the 0. Pag enter niya sa 0, wala magyapoy kaparehas. So, butang niya ang fault yapon, matawag mo siya fault. Then, after that, 1, field fault yapon. Then, pag sulod sa 2, dire na magamit ang first, dire na siya magamit ang first in, first out. So, kato ang longest nga number nga nagamit. So, or the first nga nagibutang sa page, 7 man. So, pagsulod sa muna iyang nag-replace sa 2 kay ang first nga gisulod mo i-replace kung mosulod na ang number 2. So, muna siya 201. So, after na 0. So, kining walay page diri nga 0 yang tungod. Kinatawag na siya hit kay kung isulod na ang 0 sa page, na may 0 sa page. So, same lang yapon ang butang diri sa blank. 201 yapon ni siya na diri. Then, mura yapon same process. Kasi first in, first out. So next is the optimal page replacement. Belandi anomaly was the search for an optimal page replacement algorithm. This has the lowest page fault rate of all algorithms and will never suffer from validity anomaly. Such an algorithm does exist and has been called OPT or MIN. It is simply this: replace the page that will not be used for the longest period of time. So we have an example here. We have a reference string the optimal page frames algorithm is lahi lang siya sa FIFO. Kini siya is first yang gibuhat is iput niya ang 7 sa page. So may tawag siya fault. After that 0 na sad. Then fault yapon na siya tawag. Then 1 same na gyapon fault. Then kini 2 ang gibasa na ni is magtan-aw ka sa to the right ka sa 2 ka magsugod to the right. Kung asa sa ila kining 701 ang pinaka layo nga nagamit. So atong primero na right paingon 0 nakita no 0. Next 0, next 1 kita na tong 1 na. So ang pinakalayo sa iya is 7. So mo nang 7 atong gi-replace sa 2. So mo nang 201. After gi-input, after na kining na blank nga page nga frame is same lang gyapon kay kung input mo 0 na naman 0 gyapon ito, so same ra sila. Mo nang gitawag nga hit. So after na input niyang 3. So tan-aw na pud siya sa left to right. Tan-aw niya ang 201 kung asa ang pinakalayo. So 0, kita na 0, 2, ito, o 3. So dira na makita dayon. So inana lang ang pagkuan sa algorithm. Magtan-aw ka sa left ay right, magtan-aw ka sa right kung asa ang pinakalayo nga number sa ilang tulo mo imong pulihan. So next is the LRU page replacement. LRU replacement associated with each page the time of that page last used. When a page must be replaced, LRU chooses the page that has not been used for the longest period of time. An LRU page replacement algorithm may require substantial hardware assistance. The problem is to determine an order for the frames defined by the use of time. So we natay duha ka implementation, the counter and the stack. First is the counter. So natay example ni reference string gapon, then the page frame. Yang algorithm ani is to the left siya. To the left. So first input niyang 7 fault tawag, then 0, after ana is 1, then if i-replace niyang 2, sulod na niyang 2 sa frame, tanawon niya dito ang pinakalayo katong sa optimal is dito sa right, kini siya dito ni siya sa left imong magtan-aw ani. So ang pinakalongest nga nagamit kay ang 7 man pinakalayo nga na yang na counter. So 7 imong i-replace. After na isulod niya ang 0. So same lang gyapon. So kining na blank na diri is same lang gyapon sa 201. After ana is input niya ang 3 sa page frame. So tanaw na pud niya na kung asa ang 201 nga pinakalayo. So tanaw niya 0, encounter niya 2, encounter gyapon niya. Pagsunod sa 2, 1 ang pinakalas nga pinakalayo. So 1 yang ibaylo, i-replace. So munang 203. So after and so on. Next is the stack. In this way, the most recently used page is always at the top of the stack, and the less recently used is always at the bottom. LRU replacement does not suffer from Belandi anomaly. A stack algorithm is an algorithm for which it can be shown in the set of pages in a memory and frames is always of a subset of the page that would be in memory with n plus 1 frames. So same lang yapon sa counters. Ang sa stack lang is ang iyang pangitawon most recently used kay dito sa top, then yang list kay sa bottom. So same lang gyapon ang process ato. Paingon ka sa taas pag mo replace ka or pag tan-aw na ka sa iyang algorithm. So next is the LRU approximation page replacement. Unfortunately, full implementation of LRU requires hardware support, and a few systems provide the full hardware support necessary. In many systems provide a reference bit. This is the entry in a page of the table, which is set up anytime that page is accessed. Initially, all bits are set to 0. They can also all be cleared at any time. 1 bit of precision is enough to distinguish pages that have been accessed since the last clear from those that have not, but does not provide any finer grade of detail. So this is an additional reference bits algorithm. First is record reference bits at regular intervals. It keeps 8 bits for each page in a table in a memory. Periodically shift reference bit into higher order bit. Then during a page replacement, interpret the 8-bit as unsigned integer. The page with the lowest number is the LRU page. So this algorithm is the second chance algorithm. So same lang gyapon isa sa FIFO replacement. Nasa gamit sa reference bit. So ang nakalainan niya dani kay tagaan siya og second chance nga pag-access ato. So if the reference bit is 0, replace the page. If the page to be replaced in clock order has been reference bit is equal to 1, then set reference bit to 0. So muna siya ang implementation sa second chance algorithm. Sa instructor pa ni is matawag ni siya sa circular single linked list. Ani siya. So enhanced second chance algorithm need a reference bit and a modified bit as an order pair. Therefore, situations are possible. First, 00 neither recently used or modified piece page to replace. 01 is not really used, not modified, not quite as good because the page will need to be written out before replacement. Number 3 is 10. Recently used but clean, probably will use again soon. Then the 4, it will modify, probably will be used again soon, and the page will be need to be written out to this before it can be replaced. So this is the counting page replacement. It keep a counter of the number of page reference that have been made to each page. So natay duada ni is LFU, which means less frequently used algorithm. It will replace page with smallest count. Then iyang rationale is frequently used page should have a larger reference count. Then yung variation is shift bits, right? Next is the MFU, the most frequently used algorithm. So replace pages with highest count based on the argument that the page with the smallest count was probably just brought in and has yet to be used. Next is the page buffering algorithm. It keeps pulls of free frames. So when a page fault occurs, choose the victim frame, desired page is read into free frame from pool before victim is written out. Allows process to restart soon. Victim is later written out and added to the free frame. Second is maintain list modified pages. When paging device is idle, write modified page to this and clear modified bit. Third, keep frame contents in pool of free frames and remember which page was in frame. If desired frame, if desired page is in free frame pool, no need to page in. Next and the last is the application and page replacement. All of these algorithms have OS guessing about the future page access. Some applications have better knowledge, like database, then the memory intensive application can use in the double buffering. First is the OS keeps copy of page in the memory as input output in the buffer. Next is the application keeps page in memory for its own work. Then the operating system can be given direct access to the disk, getting out of the way of applicants. Then muna siya, the root disk mode, and the lastly is the bypasses the buffering clock.
We turn next to the issue of allocation, which is allocation of frames. So what is allocation of frames? Allocation of frames are used if you have multiple processes. It helps decide how many frames to allocate to each process. For example, if there are 50 free frames and 5 processes, how many frames does each process get? In pure demand paging, all the 50 physical frames are in the list of free frames. During execution, page faults occur and necessary pages are brought into the free frames. If there is no free frame, a page replacement algorithm is used. After termination of a process, the frames that the process used are added back to the free frame list. There is another variant where free frames are always kept available. When there is a page fault, a victim page is selected, but before moving out the victim page, the required page is moved into one of the free frames. The victim page is later moved out and the corresponding frame where the victim page was kept is moved to the list of free frames. So there are few constraints while allocating frames. It is not possible to allocate frames more than the total number of available frames. So it is also needed that each process must be allocated at least a minimum number of frames. So this is because when the number of frames allocated to a process decreases, page fault rate increases. Next is minimum number of frame. There are various constraints to the strategies for the allocation of frames. You cannot allocate more than the total number of available frames. At least a minimum number of frames should be allocated to each process. These constraints is supported by two reasons. The first reason is, as less number of frames are allocated, there is an increase in the page fault ratio, so decreasing the performance of the execution of the process. Secondly, there should be enough frames to hold all the different pages that any single instruction can reference. Suppose the instruction set supports one level of indirect level addressing, then a minimum of 3 frames must be allocated per process. So if there are multiple levels of indirection, then there are more problems. Hence, it is necessary to place a limit on the levels of indirection. So next is allocation algorithms. Under allocation algorithms is equal allocation, which is each process gets the same number of frames. Divide the frames equally between the processes. So m frames divide n processes. So for example, if there are 93 frames and 5 processes, so 93 frames divide 5 processes, each process will get 18 frames. So the 3 leftover frames can be used as a free frame buffer pool. So ang next is proportional allocation. So proportional allocation, it allocate frames according to size of process. So Si is equal to size of process Pi. Then S is equal to summation of SI. Then ang M is equal to the number of frames. Then ang AI is equal to the allocation for PI equals SI over S times M. So for example, where M is equal to 64, suppose there are two processes P1 and P2. Let the size of process P1 be S1 is equals to 10. So let the size of process P2 be S2 is equals to 127. The number of frames allocated to process P1 is A1. So ang S1 na to sa A1 is 10. Then ang S dayon na to is S1 plus S2. So which is 10 plus 127. So mo nang 137 siya. Then times sa 64. So equals dayon si 5. Then the number of frames allocated dayon sa process P2 is A2. So ang S2 na to is 127, gi-divide siya sa 137 nga S, and then gi-time siya sa 64 nga M. So equals sa 159. So next is priority allocation. So in this method, frames are proportionally allocated using priorities rather than the size. So it is possible to allocate frames based on a combination of size and priority. So if ang process PI generates a page fault, select for a replacement one of its frames. Then select for replacement a frame from a process with lower priority number. So next is global versus local allocation. So global replacement is a process selects a replacement frame from the set of all frames, even if that frame is currently allocated to some other process. That is, one process can take a frame from another. So ang local replacement, it requires that each process select from only its own set of allocated frames. So ang global replacement gives better throughput than ang global replacement is mo na ang commonly used. Next is non-uniform memory access. So it is systems in which memory access times vary significantly are known as non-uniform memory access or NUMA. Collectively as systems and without exception, they are slower than systems in which memory and CPUs are located on the same motherboard. Managing which page frames are stored at which locations can significantly affect performance in NUMA systems. If we treat memory as uniform in such a system, CPUs may wait significantly longer for memory access than if we modify memory allocation algorithms to take NUMA into account. Similar changes must be made to the scheduling system. The goal of these changes is to have memory frames allocated as close as possible to the CPU on which the process is running. The definition of close is with minimum latency, which typically means on the same system board as the CPU. So for example, a process with many running threads may end up with those threads scheduled on many different system boards. How is the memory to be allocated in this case? So Solaris solves the problem by creating an entity in the kernel. Each one group gathers together close CPUs and memory. In fact, there is hierarchy of one groups based on the amount of latency between the groups. Solaris tries to schedule all threads of a process and allocate all memory of a process within one group. So if that is not possible, it picks nearby one group for the rest of the resources needed. So in this manner, overall memory latency is minimized and CPU cache hit rates are maximized. Next is thrashing. In fact, if a process does not have enough pages, the page fault rate is very high. So this leads to suspend the process execution, page out remaining process, and introduce a swap in a swap out level. Process does not have enough frame to support pages. So thrashing is a process is PC swapping pages in and out. So next is cost of thrashing. So the operating system monitors CPU utilization. We increase the degree of multiprogramming by introducing a new process to the system. So if a process enters a new phase and its execution and needs more frames, it starts faulting and taking frames away from other processes. As processes wait for the paging device, CPU utilization decreases. Limit the effect of thrashing by using a local replacement algorithm. So we can limit the effects of thrashing by using a locality model of process execution. So with local replacement or model, if one process starts thrashing, it cannot steal frames from another process. If processes are thrashing, they will be in the queue for the paging device. So mo ni siya ang kanang ano sa thrashing. The average service time for a page fault will increase because of the longer average queue for the paging device. Thus, the effective access time will increase even for a process that is not thrashing. So to prevent thrash, we must provide a process with as many frames as it needs. A working strategy technique is used. And then define the locality model of process execution. The locality model states that as a process executes, moves from locality to locality. A locality is a set of pages that are actively used together. A program is generally composed of several different localities which may overlap. Next is working set model. Working set model is based on the locality of the process. A working set is defined which is an approximation of the program's locality. So this is the example of working set model ning naa sa right side. Let the delta is equals to working set window be a fixed number of page references. The working set refers to the set of pages in the most recent delta page references. If a page of a process is active, then that page is present in the working set of that process. If a page is not used for some time, then that page will be dropped from the working set. So this is the page reference table figure 1. The working set size of a process is the total number of pages referenced in the process in the most recent delta references. Consider the example shown in figure 1. If delta is equals to 10 memory references, then the working set at time is 1, 2, 5, 6, and 7. By time h, the working set has changed to 3 and 4. WSSI or working set of process PI is equals to total number of pages referenced in the most recent delta or varies in time. If delta 2 small will not encompass entire locality, if delta 2 large will encompass several localities, if delta is equals to infinity will encompass entire program. So compute the working set size WSSI each process in the system. D is equals to the summation of WSSI is equals to the total demand frames, where D working set is the total demand for frames. Each process is actively using the pages in its working set. If the total demand is greater than the total number of available frames, thrashing will occur. So next is page fault frequency. So to control the page fault rate, when page fault rate is high, we know that the process needs more frames. If the page fault rate is too low, then the process may have too many frames. If the actual page fault rate exceeds the upper limit, we allocate the process another frame. If the page fault rate falls below the lower limit, we remove a frame from the process. Suspend a process if the page fault rate increase.
Hello everyone, I'm Irvin Francisco and I'm here to report about memory map files. Consider a sequential read of a file on disk using the standard system calls open, read, and write. Each file access requires a system call and disk access. Alternatively, we can use the virtual memory techniques discussed so far to treat file input-output as routine memory accesses. This approach, known as memory mapping file, allows a part of a virtual addresses space to be logically associated with the file. As we shall see, this can lead to significant performance increases when performing the input-output. Working sets and page fault rates. There is a direct relationship between the working set of a process and its page fault rate. Typically, as shown in figure 9.20, the working set of a process changes over time as reference to data and code sections move from one locality to another. Assuming there is a sufficient memory to store the storing set of process, the page default rate the process will transform between peaks and valleys over time. This general behavior is shown in figure 9.22. A peak in a page fault rate occurs when we begin demand paging a new locality. However, once the working set of this new locality is in memory, the page fault rate falls. Then, when the process moves to a new working set, the page fault rate rises toward a peak once again, returning to a lower rate once the new working set is loaded into memory. The span of time between the start of one peak and the start of the next peak represents the transition from working set to another. Then, 9.7.1 The basic mechanism. Memory mapping A file is accomplished by mapping a disk block to a page or pages in memory. Initial access to the file proceeds through ordinary demand paging, resulting in a page fault. However, a page-sized portion of the file is read from the system into a physical page. Some systems may optionally to read in more than page-size chunk of a memory at a time. Subsequent reads and writes of the file are handled as routine memory accesses, thereby simplifying file access and usage by following the system to manipulate files through memory rather than incurring the overhead of using the read and write system calls. Multiple processes may be allowed to map the same file concurrently. To allow sharing of data, writes by any of the processes modify the data in virtual memory and can be seen by all others that map the same section of the file. Given our earlier discussions of virtual memory, it should be clear how the sharing of memory map sections of memory is implemented. The virtual memory map of each sharing process points to the same page of physical memory, the page that holds a copy of the disk block. In the figure 9.23, the memory mapping system calls and also support copy on write functionality, allowing the processes to share a file in a read-only mode but to have their own copies of any data they modify so that access to the showed data is coordinated. The processes involved might use one of the mechanisms of achieving mutual exclusion described in Chapter 6. Shared memory in the Win32 app. The general outline for creating a region of shared memory using a memory map files in the Windows 32 API involves first creating a file mapping for the file to be mapped and establishing a view of map file in a process's virtual address space. A second process can then open and create a view of the map file in its virtual space. The map file represents the shared memory object that will enable the communication to take place between the process. To establish a memory map file, first is the file is mapped with the create file function, which returns a handle to the open file. Then the next process is using the create file map function, where it creates a mapping of this file handle. Then, once the file mapping is established, the process then establishes a view of map file in its virtual address space with the map view df file. The view of the map file represents the portion of the file being mapped in the virtual address space of the process. The entire file or only a portion of it may be mapped. We illustrate the sequence in the program shows in figure 9.25. The call to create file mapping creates a named shared memory object called shared object. The consumer process will communicate using this shared memory segment by creating a mapping to the same name object. The producer then creates a view of the memory map file in its virtual address space. By passing the last three parameters the value 0, it indicates that map view is the entire file. It could instead have passed values specifying an offset and size, thus creating a view containing only a subsection of the file. The map view of file function returns a pointer to a shared memory object. Any access to this memory allocation are thus access to the memory map file. In this instance, the producer writes the message shared memory message to shared memory. A program illustrating how the consumer process establishes a view of the named shared memory object shown in figure 9.26. This program is somewhat simpler than the one shown in figure 9.25, as all that is necessary is for the process to create a mapping to the existing named shared memory object. The consumer process must also create a view the map file, just as the producer process did in the program in figure 9.25. The consumer then reads from shared memory the shared memory message that was written by the producer process. Finally, both processes remove the view of the map file with a call to unmap view of file. We provide a program exercise at the end of this chapter using shared memory with memory mapping in the Windows 32 API. Then, memory map I/O. In the case of input-output, as mentioned in section 1.21, each input-output controller includes registers to hold commands and the data being transferred. Usually, special input-output instructions allow data transfers between these registers and system memory. To allow convenient access to input-output devices, many computer architectures provide memory map input-output. In the IBM PC, each location on the screen is mapped to a memory location. Displaying text on the screen is almost as easy as writing the text into the appropriate memory map locations. Memory map input-output is also convenient for other devices, such as the serial and parallel ports used to connect modems and printers to a computer. The CPU transfers data through these kinds of devices by reading and writing a few devices registers called an input-output port. If the CPU uses polling to watch the control bit, constantly looping to see whether the device is ready, this method of operation is called the program input-output, or PIO. If the CPU does not pull the control bit, but instead receives an interrupt when the device is ready for the next byte, the data transferred is said to be interrupt-driven. 9.8. Deallocating kernel memory. When a process running in user mode requests additional memory, pages are allocated from the list of the free page frames maintained by the kernel. The list is typically populated using a page replacement algorithm such as those discussed in section 9.4, and most likely contains free pages scattered throughout physical memory as explained earlier. There are two primary reasons for this. The first is the kernel requests memory for data structures of varying sizes, some of which are less than a page in size. As a result, the kernel must use memory conservatively and attempt to minimize waste due to fragmentation. This is especially important because many operating systems do not subject kernel code or data to the paging system. And second is pages allocated to user mode processes do not necessarily have to be in contiguous physical memory. However, certain hardware devices interact directly with the physical memory without the benefit of a virtual memory interface, and consequently may require memory residing in physical contiguous pages. In the following sections, we examine two strategies for managing free memory that is assigned to a kernel process, which is the body system and the slab allocation. The body system. The body system allocates memory from a fixed size segment consisting of physical contiguous pages. Memory is allocated for this segment using a power of 2 allocator, which satisfies requests in units sized as a power of 2, 4 kilobyte, 8 kilobyte, 16 kilobyte, and so forth. A request in units not appropriately sizes is run out to the next highest power of 2. For example, if a request for 11 kilobyte is made, it is satisfied with a 16 kilobyte segment. Then, let's consider a simple example. Assume the size of the memory segment is initially 256 kilobyte and the kernel requests 21 kilobyte of memory. The segment is initially divided into two bodies, which we call AL and AR. each 128 kilobyte in size. One of these bodies is further divided into two 64 kilobyte bodies, BL and BR. However, the next highest power of 2 from 21 kilobyte is 32 kilobyte, so either BL or BR is again divided into two 32 kilobyte bodies, CL and CR. One of these bodies is used to satisfy the 21 kilobyte request. This scheme is illustrated in figure 9.27, where CL is the segment allocated to the 21 kilobyte request. As we can see in the figure 9.27, an advantage of the body system is how quickly adjacent bodies can be combined to form a larger segment using the technique known as coalescing. In figure 9.27, for example, when the kernel realizes the CL unit it was allocated, the system can coalesce CL and CR into a 64 kilobyte segment. In fact, we cannot guarantee that less than 50% of the allocated unit will be wasted due to internal fragmentation. In the following section, we explore a memory allocation scheme where no space is lost due to fragmentation. Then, the slab allocation. A second strategy of allocated memory is known as slab allocation. A slab is made up of one or more physical contiguous pages. A cache consists of one or more slabs. There are single cache for each unique kernel data structure. For example, a separate cache for the data structure representing process descriptors, a separate cache for file objects, a separate cache for semaphores, and so forth. In the figure 9.28 slab allocation, the figure shows two kernel objects, 3 kilobyte in sizes, and the 3 objects in 7 kilobyte in size. The number of the objects in the cache depends on the size of the associated slab. For example, a 12 kilobyte slab made up of 3 contiguous 4 kilobyte pages could store 6 2 kilobyte page objects. Initially, all objects in the cache are marked as free. When a new object for a kernel data structure is needed, the allocator can assign any free object from the cache to satisfy the request. In Linux, a slab may be one of the three possible states. First is the full, second is the empty, and the third is the partial. The slab allocator first attempts to satisfy the request with a free object in a partial slab. If none exists, a free object is assigned from an empty slab. If no empty slabs are available, a new slab is allocated from contiguous physical pages and assigned to a cache memory for the object is allocated from this slab. Then, the slab allocator provides two main benefits. First is no memory is wasted due to fragmentation. Then secondly is memory requests can be satisfied quickly. The slab allocation scheme is thus particularly effective for managing memory when objects are frequently allocated or deallocated, as is often of the case with requests from the kernel.
So good day guys. The topic of our group is virtual memory management, and this is my topic. So my topic is other consideration, which covers the prepaging, page size, TLB reach, inverted page tables, program structures, in and out interlock, and the operating system, which covers Windows and Solaris. So let's begin. Prepaging. Prepaging is to reduce the large number of page faults that occurs at process startup. Prepage all or some of the pages a process will need before they are referenced. But if dili magamit ang prepage guys, ang in and out and memory kay masayang. So makita ninyo siya that assume S pages are prepared and A of the pages is used. Tara guys, so makita niyo siya guys, if dili niyo siya magamit is masayang gid siya. So next is page size. Page size affects the amount of memory needed and space used when memory needed and space used when running programs. Most operating systems determine the page size when program begins running. This feature allows it to calculate the most efficient use of memory while running that program. So ang page size guys is na siya gina-consider, which are fragmentation, page table size, which is to keep it relatively small. We need kailangan man siya bigger pages, and in and out overhead, which latency, throughput characteristic called by bigger pages, and then locality guys, if better will with smaller pages because of better resolution. Next, TBL reach. So TBL reach the amount of memory accessible from the TLB na siya guys. So ideally the working of so tara ang kuan guys, makita ninyo dara ang kanang computation so on po ko ang TLB. Then ideally the working set of each process is stored in the TLB. Otherwise, there is a high degree of page faults. And increase the page size. This may lead to an increase in fragmentation, as not all application requires a large page size. Then provide multiple pages size. This allows applications that require larger page size the opportunity to use them without any increase in fragmentation. Next is the program structure. So as you can see guys, naggamit siya og two-dimensional arrays. So the program whose function is to initialize to 0 each element of a 128 by 128. So makita ninyo siya guys diri sa program 1. So manotice ninyo siya guys that the array stored is row major, that is stored data 00, data 01, and so on. So for pages of 128 words, each row takes another word in each page, and so on. If ang operating system allocates fewer than 128 frames to the entire program, then ang execution will result 128 times 128. So muna siya guys, 16,384 page faults. Then the program 2 guys is gibago siya code, ay dara siya gi-swap ang I ug ang J nga variable. Then this code zeroes all the word in one page before starting the next page. So nag-reduce siya the number of pages faults to 128 na lang siya guys. So in and out interlock. So pages must sometimes be blocked into memory. Consider in or out pages that are used for copying a file from a device must be locked from being selected for eviction by a page replacement algorithm. Pinning of pages to lock into memory. There siya guys. So kung kay siya guys, risky kay siya kung mag-lock ka. Dayon, ang next topic kay operating system examples, which is Windows. So Windows uses demand paging and clustering. Clustering brings in a pages surrounding the faulting page. Processes are assigned working set minimum and working set maximum. And working set minimum is the minimum pages of the process is guaranteed to have in memory. A process may be assigned as many pages up to its working set maximum. When the amount of free memory in the system falls below the threshold, automatic working set trimming is performed to restore the amount of free memory. Working set trimming removes pages from processes that have pages in excess if their working set minimum. Next is the operating system example siya siya guys under ang Solaris. So ang Solaris is maintain a list of free pages to assign faulting process. That's free threshold parameter, amount of free memory to begin paging. That's free threshold parameter to increasing paging. Min free threshold parameter to being swapped. Paging is before performed by page out process. Page out scans page using modified clock algorithms. Scan rate is the rate of which pages are scanned. These ranges of slow scan to fast scan. Page out is called more frequently depending upon the amount of free memory available. Priority paging gives priority to process code pages. So, kana sila guys is gina-define kung unsa ilang gamit sa salaries. Then, kani siya nga picture guys is as the mention unsay ay as nakita ninyo sa unsay nasa pic. The page out process checks memory for 4 times per second. However, if the free memory falls below this free, which is na kaning kuan, page out will run 100 times per second with intention of keeping at least this free memory available. If the page out process is unable to keep the amount of free memory for 30 seconds average, the kernel begins swapping process, thereby freeing all pages allocated to swap process. In general, the kernel looks for processes that have been ideally for a long period of time.
Chapter 9 Visual Memory Management 9.11 The Summary. It is desirable to be able to execute a process whose logically addressed space is larger than available physical address space. Virtual memory is a technique that enables us to map a large logically addressed space into larger physical memory. Virtual memory allows us to run extremely large processes and to raise the degree of multiprogramming. It increases CPU utilization. Further, it frees application programmers from worrying about the memory ability. In addition, with virtual memory, several processes can share system libraries and memory. Virtual memory also enables us to use efficient type of processes creation known as copy on write, wherein parents and child processes share actual pages of memory. Virtual memory is commonly implemented by demand paging. Pure demand paging never brings in a page until the page is referenced. The first reference causes page to fall to the operating system. The operating system kernel consults an internal table to determine where the page is located at the backing store. It then finds a free frame and reads the page in from the backing store. The page table is updated to reflect in this change, and instruction that cause the page fault restarted. This approach allows a process to run even though its entire memory image is not a main memory at once. As long as the page fault rate is reasonably low, performance is acceptable. We can use demand paging to reduce the number of frames allocated to a process. This arrangement can increase the degree of multiprogramming, allow more processes to be able for execution at one time, and in theory, at least the CPU utilization of the system. It also allows processes to be run even though their memory requirement exceed the total number of available physical memory, such as processes run in virtual memory. If the total memory requirements exceeds the capacity of physical memory, then it may be necessary to replace pages from the memory to free frames for new pages. Various page replacement algorithms are used, such as FIFO page replacement is easy to program but suffers from Beladi's anomaly. Optimal page replacement requires the future knowledge. LRU replacement is an approximation of optimal page replacement, but even it may be difficult to implement. Most of the page replacement algorithms such as second chance algorithm are approximation of LRU replacement. In addition to a page replacement algorithm, a frame locally policy is needed. Allocation can be fixed suggesting local page replacement or dynamic suggesting globally replacement. The working set model assumes that processes execute in localities. The working set is the set of pages in the current locality. Accordingly, each process should be allocated enough frames for its current working set. So if a process does not have enough memory for its working set, it will trash. Providing enough frame to each process to avoid trashing may require process swapping and scheduling. Most operating systems provide features for memory, such as mapping files, thus allowing file I/O to be treated as a routine memory access. The Win32 API implements shared memory through memory mapping files. Kernel processes typically require one memory to be allocated using pages that are physically contiguous. The body system allocates memory to kernel process in unit size according to a power of 2, which often results fragmentation. Slab assign kernel data structures to cache associated with slabs, which are made one of more physically contiguous pages. With slab allocation, no memory is wasted due fragmentation and memory requests can be satisfied quickly. In addition to requiring that we solve the major problems of page replacement and frame allocation, the proper design of a paging system requires that we consider preparing page size, TLB, reach, inverted page tables, program structure, IO interlock, and other issues.